A2. Steam plants. This section cover the fundamental parts of a ship's steam plant, except for those items of equipment which are grouped together in other sections, because they are common to the steam and diesel engine plants. In maritime history, as in other land-based activities, steam is the medium through which the industrial mechanization of the 19th century took place, becoming the sole means of propulsion of ships until the diesel engine came to be introduced well into this present century. The 1974 oil crisis, with the jump in fuel prices, was a strong blow to high boiler consumption levels, especially since diesel engines are using heavier and heavier fuels. Nevertheless, a notable effort is being made in improving the performance of steam plants, on the one hand by better utilization of the steam cycle, and on the other, with the incipient return to coal, which a number of ships are also using. The attached figure shows a diagram of a typical marine steam plant. In the boilers, the area of the plants where the steam is produced, two different zones must be distinguished, as can be seen in the attached figure. High-temperature gas is produced in the firebox, combustion chamber, by burning a mixture of atomized fuel and air. This hot gas flows by steam-generating tubes of steam superheater that feed water and combustion air respectively before they are introduced into the boiler. The gas is finally exhausted via the outside stack. The water system already heated in the economizer absorbs the heat produced by combustion through the heating surface, steam-generating tubes, drum, etc., where the water is vaporized. The steam produced is a saturate steam that leaves the boiler through the separator and is normally reheated in the superheater, going off to be used in the main engine. Some of the auxiliary engines work on desuperheated, giving off part of its heat to the boiler water. The following figures show some examples of different types of boilers. Presentations are communication tools that can be used as demonstrations, lectures, speeches, reports, and more. Most of the time, they're presented before an audience. It serves a variety of purposes, making them powerful tools for convincing and teaching. The turbine is the steam plant component that transforms the plant's heat energy into mechanical energy. The attached illustrations provide a representative diagram of a normal turbine installation for driving a ship, along with details of the turbines themselves. Here we have the structure of three types of turbines. The high-pressure turbine, smaller in diameter and length, the low-pressure turbine, where one can see the considerable increase in diameter for steam expansion, and the astern turbine mounted on the shaft of the latter. Both the high-pressure turbine shaft and the low-pressure turbine shaft are engaged through flexible connections to the high-velocity shafts of the reducing gear. The latter transmits power through the intermediate shafts and the low-speed gear to the drive shafts and the low speed to the drive shaft that moves the propeller. In addition to the boiler and the turbines, being main items of equipment of the steam plant, the latter has a large number of auxiliary components such as condensers, ejectors, deaerator. There are also other types of machinery on board, other than the steam-powered main turbines. Thus, we have the turbopumps for various uses, the turboalternators to generate electricity and the reciprocating engines, chiefly need for deck equipment and stripping pumps. Finally, we should mention the gas turbine, widely used in the Navy because of its small size and which is sometimes installed on merchant ships to drive the standby generator sets, though it is necessary to mention the disadvantage of its high fuel consumption. Following are some points of information and practical cases useful on ships. 1. Boiler testing and controls. A boiler undergo the hydraulic pressure test relatively frequently on board ship, at least in order to detect leaks and to check watertightness after certain repairs. When this test is conducted, all possible air pockets should be eliminated so that the boiler will be completely filled with liquid and so that all leaks can be located. If the leak were in the areas occupied by the air, they would not be easily detected. B. It is generally known that leaks in a boiler are in the area of water, due to the sedimentation of additives for chemical treatment. To locate these leaks, a hydraulic test will be conducted only in the above-cited area. It should be borne in mind that when there are internal desuperheaters in the boiler drums, these should be in communication with the liquid being used for the test, to balance internal and external pressure. If this is not done, the desuperheater would collapse, since it is not designed to withstand great pressure. C. The pressure gauges usually used in steam plant installations are so-called metal or Boudon gauges. This gauge consists of a tube of elliptical cross-section sealed at its free end, with the other fixed end set up for the intake of the liquid. As the internal pressure of the tube tends to straighten itself out and, through certain mechanisms, it transmits its movement to a needle that moves over graduated scale on which the pressures are indicated, thereby giving the value of the pressure measured. Metal pressure gauges are graduated by comparison with a standard gauge. 2. Water and steam compounds and treatments. A. Water whose pH is equal to 7 is called neutral. A higher pH reading indicates that the water is alkaline and a lower reading indicates that it is acid. All the ferrous components of the ship will sustain very strong corrosive action in the presence of acid waters. In order to reduce or eliminate this serious problem, it will be necessary to treat the water with products that increase its alkalinity. B. Boiler manufacturers normally do not permit any type of hardness in the boiler feedwater. Hard waters are those that contain chiefly magnesium and calcium, and are the cause of the formation of scales in the boilers, since as the water temperature rises, these elements become insoluble. Normally, the hardness of the water can be checked with a reagent that foams when all the salts that cause the above-mentioned hardness are precipitated. C. The dissolved solids are molecular scale substances, ions, that are invisible to the eye, though in some cases, they can cause some chlorine. Their pressure is verified by the conductivity of the liquid that contains them, and they cannot be eliminated by filtering. On the other hand, solids in suspension can be eliminated. D. Since the solids dissolved in the water are in the form of ions, the water acquires greater conductivity to electric current when there is a greater pressure of these ions. Therefore, it is normal for high-pressure boilers to have a conductivity meter installed. In this manner, the monitoring can be constant or very frequent, and it is therefore possible to take quick action to correct water contamination. E. If the superheater tubes of a boiler are dirty, heat transmission will be reduced. And so will steam temperature of the superheated steam can be due to the following cause, among others. A higher than normal feedwater temperature, which will cause a drop in the temperature of the steam because of the decrease in the fire necessary to evaporate the water. Low maintenance of the volume of air injected for combustion. This is a sign of poor combustion, with a consequent drop in the temperature of the superheated steam. When the steam pressure is low at constant power, this problem will be offset by a larger amount of steam, so that there will be a greater consumption of calories with a corresponding drop in temperature. F. In boiler with a working pressure of more than 60 kg per square centimeter, one of the most dangerous solids that can accompany the steam is silica, because it vaporizes under circumstances. It adheres readily to the blades of the turbine rotor, forming some very hard scales that are difficult to remove. When the pressure is below the figure indicated above, the silica does not vaporize and can be removed from the boiler only by solid scouring, so that it is less dangerous than in the other case. 3. Combustion. When reducing the firing rate of a boiler, the fuel flow, to prevent that part of the atomized fuel remain unburned. This fuel, falling to the bottom of the firebox, could cause, in addition to spontaneous combustion with its unfortunate consequences, a large quantity of smoke, dirtying the boiler and reducing its performance. B. The attached figure shows a diagram of the head of a burner where one can see how the fuel to be burner comes in through the central conduit, is pulverized in the atomizer and goes out the nozzle to be burned inside the firebox. The remaining fuel then returns through the lateral conduits to the return system, as the flow of fuel is limited by the nozzle orifice. 4. Firing. During the firing of a boiler with automatic control, it should be recalled that the forced draft fan must always be started with the air suction blades closed, to dampen the effects of the strong starting torque of the drive motor. Before each firing, any possible gases that may be found in the firebox and the boiler ducts must be scavenged. This will be done with the fan in operation and with the suction blades open as wide as possible in order to achieve an energetic sweeping of any gases that may be present. During the firing periods, it is customary to maintain a differential pressure of 15 mm water column between the distribution duct and the furnace, in order to give intake velocity to the air entering the firebox through the diffuser cone, and thus to mix the air with the fuel that emerges atomized from the burner nozzle. B. During firing, it is advisable that boiler warm-up be as uniform as possible. To do this, it will be necessary to rotate the firing of the burners and control the time that each one is to be fired according to the plan set forth ahead of time. This plan will take into account the time available to have the boiler lined up with the services and, if the refractory material was recently e-paired, the need to extend the warm-up period. 5. Operation and control. To facilitate a summary of the sequence of flows in a boiler, already referred to at the outset of this topic, simplified diagrams like the one shown in the attached figure are occasionally used. 6. Boiler safety valve. When a safe valve is installed in a boiler after it has been examined or adjusted, it is necessary to make sure its opening is a minimum of 1/4 of the nominal diameter of the seat of the plug. Otherwise, its venting capacity will be reduced, and this can cause an accumulation of pressure with grave consequences. This is due to the fact that the nominal area of the plug seat cannot be greater than the venting area, as can be seen in the attached illustration. 7. Water levels. When a boiler is being filled up for firing, it should be left at a level somewhat lower than normal, because when the burners are ignited, the rise in water temperature makes its volume increase. In addition, as the boiler firing rate is increased, and therefore, its steam production, increases, the size of the bubbles produced will increase, also raising the water level. A reduction in boiler firing rate will cause the opposite effect. B. When a boiler has only a little water left in it, the burners should immediately be turned off. In no case should water be fed before the boiler cools down. If water is fed suddenly, it could cause the boiler or one of its components to burst, because when the water comes into contact with the superheated metal, it is instantaneously evaporated. 8. Boiler drums. The steam produced by the boilers is purified, before leaving the boilers, in the steam separators that are usually found in boiler at the highest portion of the steam drum connected to the steam line. These separators eliminate both the moisture and any solid particles from carrying over into the superheater. B. When the taper of a seat of the manhole of a drum is greater than 0.1 mm, it should be re-machined at right angles to the opening to prevent leaks through the weakest points. In addition, when a drum cover is about to be installed, molybdenum disulfide is normally applied to the bolts and nuts of the covers, especially those subjected to high temperatures, to facilitate their subsequent disassembly.